I am Jean-Marc Salotti. I think you already know that, but perhaps what you don't know is that I'm professor in university called Bordeaux INP, and it's a university that where you can find several schools, engineering schools, and one of them is Ecole Nationale, Supérieure de Cognitique. It's about human factors and artificial intelligence and decision making, human systems interactions. That's our engineering school. And also, of course, I'm from Association Planet Mars. All right, so I'm going to talk about the air composition in Martian habitats. This is probably a hot topic. Probably you don't know that it is a hot topic, but I'm going to tell you, to explain you that it is a hot topic. So, just introduction, there is, only 3 parts, and then the conclusion. Maybe you know that for the International Space Station, the composition of the air is 78% nitrogen, 21% oxygen, 1 bar. This is what we have on Earth. So it's very easy. You go in the capsule, you go to the International Space Station, you open the door, that's it. You come back the same. So very easy, very simple. But the problem is, as you probably know, for EVA preparation, when you want to go outside, an astronaut wants to go outside, 2 hours preparation. Why? Because in the spacesuit, you don't have 1 bar, you only have 0.3 bar, and only oxygen, pure oxygen. So, from this composition of the atmosphere, which includes nitrogen, you have to remove all the nitrogen and have and breathe with only pure oxygen. 2 hours, it's a lot. How can we imagine that? Imagine you're on Mars, so you're in the habitat. You want to go outside. Okay, 2 hours. If there is an emergency, you want to go outside for an emergency. 2 hours. No, it's not possible. You cannot imagine that, of course. So this is not the option. This is not the option. Okay, in 2024, I asked a question to a NASA person, which was in charge of the. I think it was in charge of the Artemis program. So the question was, do you know what will be the air composition and pressure of the habitat modules of the Artemis program? You're going to the moon, right? What will be the air composition inside the modules? And the answer was not decided yet. Okay, so it's strange, Artemis has started already, so and we don't know what will be the composition of the air inside the modules. Another question was to the person in charge of the ISS, NASA person. I think it was the head of the ISS anyway. So the question was, what about testing over air composition in the ISS? And the answer was, well, no, it's not possible. It's not designed for that. So I had the feeling that the ISS has been built and designed to prepare the going to the moon, to Mars and beyond. But we haven't tested the air composition in the ISS. So actually, after 20 years of ISS, we still don't know, and we haven't tested anything on board about the composition of the air. This is, I can say it's a shame, more or less. It's a shame, but we have this station and we didn't test anything on board. Yes, of course, it was not designed for that. So who decided to design? I think we should ask that person, why didn't you think that we had to test that? And maybe at some point, maybe 10 years ago, we could have said, okay, let's make some modifications, important modifications in the ISS so that we can test that. It was not done. So anyway, so next slide. Oh, just another point. I think I have to stay here because there is a there is a camera here, and they said if I'm just standing here, not possible to. Oh, it changed. But anyway, I'm going to stand here. So breathing parameters, just you can understand some basic important things about breathing. I'm not going into the details of the formulas. Probably what is important, of course, is I'm sure you know that we need oxygen, of course. We don't need nitrogen. We need oxygen for breathing. That's it. Maybe an important question is what pressure is needed for oxygen? We don't need, of course, 1 bar oxygen. We only need, in the atmosphere it's 21% of oxygen, so probably something like 210 millibars of oxygen. But in fact, when you go to the calculations, it depends. It depends on many other parameters as well. I'm not going to the details, but what you need, of course, is you have to understand is that pure oxygen is possible, and of course we know it's possible because we go in the spacesuit. It's pure oxygen. Okay, so 260 millibars is comfortable, and this is what we go with calculations. 260 millibars is comfortable. I mean, it's probably more or less like on Earth, the feeling you have for breathing, if you want. For breathing, 260 millibars is like on Earth, more or less. Of course, with much less pressure, but in terms of how much oxygen do you go to the alveoli and in your blood, okay? So, what is the minimum? It's difficult to say what is that minimum. What about the criterion? But anyway, more or less 180 is probably the minimum. It corresponds to a high altitude. You can breathe. You can go very high in the mountains, and of course you can still breathe. But of course it's more difficult. You have to. It's more difficult to breathe. Anyway, so 180 is really the minimum. Probably it's not what you are going to. If we choose pure oxygen, 260 is more acceptable. And important, if you are more than 600 millibars, there are well-known toxic effects. So, but many people believe that pure oxygen, there are toxic effects, whatever the pressure. It's wrong. It's not whatever the pressure. It's above 600 millibars. We know toxic effects, for sure. But below that, we are going let's go to the next slide. So yes, no toxic effects for durations. Oh, sorry. Of course, yes, it's for me. So what about the Apollo experience? So you have, Apollo 1, of course. I think most of you, all of you perhaps, know that there was a terrible accident in 64, I think. 67. Okay, there was a terrible accident before the going to the moon, and the three guys here, Grissom, White, and Chaffee. It was the accident. They are all dead, of course, and the reason why, be careful, it was 1 bar. 1 bar oxygen is dangerous, very dangerous. So 1 bar of pure oxygen is not a good choice, and especially if you have some materials, even more or less all materials are easily inflammable at such pressure. But we have to remember that, first of all, the first decision was, okay, it's too dangerous, pure oxygen. Let's take some nitrogen. This was the first decision. But then NASA just made a complementary study on that, and but it's complex air composition control and management, much more complex. There is an impact on EVA procedure, more complex things, and we should have another nitrogen tank, so there is impact on Mars. And second decision. Okay, no, let's come back to pure oxygen. This was the choice for the Apollo program. Pure oxygen. But only 340 millibars, not 1 bar, 340 millibars. And there were 6 successful missions, as we know. No physiological problem reported. Okay? But duration only 12 days. What about if it is longer? So I tried to find some articles, papers on that. I think I had a look, and it was very difficult to find papers and experiments in which people were asked to stay in a room with low pressure and pure oxygen. But I found one. It was in. See, this is the reason why I told you 64, because I had this reference in 1964. So there is a paper. Oh, sorry. And here is a summary of what I think the most important sentence here. So these people, one month, okay, there was 450 millibars of pure oxygen, more or less. There was a very small amount of nitrogen, but almost negligible. So it was well tolerated by the young subjects who demonstrated very few of the previously described symptoms of oxygen toxicity. So, yeah, and then there were some problems have been reported, but they did not interfere with mission completion. So for 1 month, pure oxygen, 440 millibars, 450 millibars, it seems acceptable. 1 month. Yes, just to make you laugh, perhaps. The most significant physiological change in that experiment is the increase of the mass of the people. 2 kilograms in 1 month. Anyway, so is pure oxygen an option, finally? So this is an important question. And believe me or not, there is nothing in the literature that says that there are toxic effects. We do not know. We do not know. We are lacking data on that subject. It's incredible that we don't know. So this is the reason why, if you ask experts, what is the most appropriate air composition for the Martian habitats or lunar habitats, I think he will answer, as I don't know, I'm not going to propose pure oxygen, because I don't know. I don't want to be the one who said that it is safe. We don't know. So perhaps it's not safe. I mean, safe for long duration, of course. Long duration, for instance, 6 months, 1 year. So perhaps it's not safe. Perhaps there are toxic effects. But we don't know. And so, okay. So this is the graph that you can find. I found this graph in an important report from NASA report. Anyway, so there were some questions here. So we know the toxicity of oxygen for high pressure, but below something like 500 millibars, we don't know. Okay. If it were possible, simpler air composition, simpler control, of course. No natural gas. So we can remove the gas tank, and there are mass savings, of course. Lower air pressure, so there are lower constraints on the walls, and then you can reduce the thickness of the wall, and you still have another mass savings here. And there are drawbacks. The most important drawbacks, perhaps, apart from possible toxicity effects, but toxic effects, but apart from that, there is an important drawback, is the inflammability that is increased. It is increased, yes, but not to the level that we just with the experience of the Apollo 1. So it's a level, we have to look at that, but it seems acceptable. And it was accepted for the Gemini and Apollo missions. It was accepted. It was okay. So we can make complementary analysis of the flammability of the materials and decide, yes, this material, okay, I mean, this not, and so on. But in general, it is possible. Just have to make sure that we take appropriate actions to mitigate the risks. So the conclusion is, pure oxygen is perhaps possible. It has not been tested, so we don't know. So we should ask the space agencies, perhaps the CNES, the ESA, and NASA, and so on. We have to test that. We have to test. And so what is the most appropriate pressure? I don't know. Perhaps it's 340 millibars, like For the Apollo missions, perhaps it's less, possibly 300, perhaps 260, why not? And well, of course there are impacts in terms of safety and so on, but then we have to try 2 months and check, of course, every day, which have maybe some checks, that it is safe. And try 6 months, and perhaps this is the best solution, perhaps. I don't know, we don't know, in fact. Natural gas. Be careful, it's not only hydrogen. There is another possible option, is argon. Because we can find some argon in the Martian atmosphere, so it could be used as a natural gas. For sure, whatever the choice, the total pressure should be less than 0.5 bar. Because even if you have natural gas, even if natural gas is required, then the total pressure can be less than 0.5 bar for sure. So the best air composition and pressure, we don't know. Nobody knows, in fact. And the final conclusion is, it's a shame that the question has not been addressed before. And that's it. Thank you very much.